my great pleasure to invite Professor Steve Barnett from the University of Strathclyde to deliver the first talk of the morning. It would be very embarrassing for me to make the list of fields in which Professor Barnett is considered to be an expert, and I would eat up much of his time. At some time in his career, he got interest in solving this enigmatic problem, and which has some bearing, of course, in liquid crystal science as well. And it is concerned, from our perspective, it is concerned with the interaction between radiation and liquid crystal molecules. This is a kind of much broad perspective in which Professor Barnett today will try and place our ongoing concerns. So, without any further ado, it is my pleasure to invite Professor Barnett to deliver his talk. Please, Steve.
First of all, so I hope, does that work? Oh, great. So thank you for the invitation. Also, I have to say, I see a few colleagues from Glasgow sitting in the audience, so they'll know what I'm talking about. The greatest pleasure of actually coming here at this time is that I haven't seen a tree with leaves on it since last summer. It's been quite an astonishing, not to mention, we won't even mention the rain. What I'm going to tell you about is actually it's something of an embarrassment. It's an embarrassment because it's embarrassingly simple. It looks like a problem which Maxwell must have solved, and if not Maxwell, then certainly Poynting. It feels like something that was explained to you in one of those long, boring electromagnetism courses when you were in introduction, when you were an undergraduate, when you were sort of sitting in the back and not really paying attention. It has that flavour to it. In fact, it's a problem which has had a bewildering array of scientists arguing with each other for most of the 20th century. It's a controversy which has had supposedly definitive experiments, each supporting rival theories. So it's something of a mess. And it's actually, what is the correct description of the momentum of light, say the momentum of a photon, when it's inside a block of glass? Does the momentum increase or does it decrease? It's as simple as that. So I'll tell you the story, some of the background. My colleagues, a problem like this, you don't just jump in and say, well, I'll solve this on my next research grant. It takes a bit more time. So I'll tell you about the contributions of my colleagues, Rodney Loudon and Ed Hines, as the story progresses. So the problem is the following. If you start thinking about what the momentum of light is inside a piece of glass, you very quickly come to an embarrassment that there are two obviously correct momenta, and they're not the same. So I shall start off by explaining to you why there are these two and why they're both obviously correct. Now, Rodney's insight into this was to say that maybe momentum is a bit of a woolly concept, so let's think about forces, because after all, we all know that if you integrate up a force, you get a momentum. That's of course Newton's famous second law, and the problem there is that there are two obviously correct forces as well. And for a while, he entertained the possibility that these two obviously correct forces led to the two obviously correct momenta, but it's not true. Life isn't that simple. I'll talk to you about the two forces, and this story will unfold a little bit about experiments, thought experiments. And then I wrote this small, I suspect not quite small enough. At the end of the talk, I'll tell you what the answer is. So here's how the story starts. These guys didn't use this language, but the story was started by these two. This is Hermann Minkowski. This is Max Abraham. And essentially, in the language we would currently suggest, if we think about what the momentum density of light is, you can think in terms of essentially Poynting's vector. And if we're in free space, it doesn't matter if it's essentially E cross H or D cross B, they're both fine. But of course, inside a medium, D is not the same as E, and in general, H is not the same as B. And so we have these rival suggestions for what the momentum is. Minkowski's suggestion was D cross B, Abraham's was E cross H. And if I remember correctly, The Abraham one came along first in 1908, the Minkowski one came on in 1909, and this famous Abraham-Minkowski dilemma is, which of these is actually correct? Does it matter? Well, it matters in a very simple way, and I'll try and show you in a very simple sort of scaling argument why it makes a difference. So if we start off with the energy density and integrate over our medium to get an energy, let me think about just a single photon. So my single photon, that should essentially be h bar omega. And we also know, of course, that at least on average, time average, this energy is equally shared between the electric parts and the magnetic parts. And that gives me the fact that I can write my d dot e in terms of epsilon e squared as h bar omega, or my d squared divided by epsilon goes like h bar omega, and similarly for the magnetic parts. And what that means in turn is that if I take the integral of the Minkowski momentum, I get, this is the free space momentum, of course, h bar k, or h bar omega divided by c, multiplied by the refractive index. The Abraham one, because it's e cross h, it's divided by the refractive index. So the thing to think about, if you like, the simplest way to understand this is that in free space, the momentum of a photon is just h bar k, h bar omega divided by c. The Minkowski momentum is greater than the free space value by the refractive index. The Abraham one is less by the refractive index. So the simple question is, to get the momentum of a photon inside a piece of glass, do you multiply by the refractive index or do you divide? Now, of course, there are some regions of the spectrum, in the infrared, for example, where you can get solid-state materials which are essentially transparent, and n can be 10. So you're talking about a factor of 100 difference between these two. This is a huge effect. So which one's right? So let me prove to you that the Abraham momentum is the correct one. And to do this, I'm just going to use a very simple principle, which essentially is how aptly Newton's first law of motion. This one, that was the one about the uniform motion, modified only slightly to think in terms of not uniform motion of the center of mass, but uniform motion of the center of energy, mass energy, the relativistic form. So let me start off. Let's suppose I've got a pulse of light, some light coming in here. This is a single photon with energy h bar omega, and a piece of glass with mass m, which is stationary. And I send the light through the glass. I don't know exactly what it's doing in there, but let's suppose that I've got some timing mechanism, or I anti-reflection coat the glass, so there's no reflection at the front surface, there's no reflection at the back surface. All that happens is the light goes in and then comes out again. Now, because light travels more slowly in a dielectric medium than it does in air, afterwards, of course, the block of glass is stationary again, and the photon is less far on than it would have been if it had traveled in free space. It's retarded somewhat. And that means that in order for the center of mass energy to have been a uniform motion, the block of glass must have moved a tiny bit to the right. It must have moved in this direction. And then we can do a simple calculation. We can say, how far has it shifted? Well, it shifted by an amount delta z, and this is the energy, mc squared. And that's got to be equal to this distance here multiplied by h bar omega. And of course, that's just the thickness of the glass, L, times the refractive index minus 1. So there's my shift, absolutely tiny. Of course, it's got h bar omega, the energy of the photon, divided by the rest mass energy of the glass. It's tiny, but nevertheless, that's what it is. And of course, I also know how fast the photon was going through the glass, so I can calculate what the momentum of the block of glass was while the light was moving through it. It's a very simple calculation. It turns out to be 1 minus 1 over n times h bar omega. If that's the momentum of the block of glass, the rest must have been the momentum of the photon. Conservation of momentum, 1 over n h bar omega, which is the Abraham momentum. All I've used in this analysis is the fact that light slows down in glass essentially by the refractive index, and the center of mass of the combined system moves in uniform motion. So this must be correct. So at this stage, I could actually stop, take the applause, and carry on, were it not for the fact that I can prove to you the other one's right as well. Oh, incidentally, if I'd done this analysis with the Minkowski momentum, the block of glass would have moved in the wrong direction, of course. So that's wrong. So think about this example. This is a diffraction pattern, which we all know and love. A single slit, you get some sink-type pattern, of course, and you get this sort of opening angle. And we know how to estimate this opening angle. What you do, well, one way to do it is to say, well, if we've got a plane wave travelling in the z direction, this opening is caused by the fact that we get a spread of momenta in this transverse direction, in this x direction. So I can write this opening angle essentially as delta px, the spread of this momentum in this direction, divided by the momentum in the forward direction. And if the slit is not too narrow, that's a very good way of doing it. Then I can use the uncertainty principle. I can say delta px is h bar divided by delta x, that's the thickness of the slit, multiplied by the momentum in the forward direction, which essentially is h bar k, or h bar omega divided by c. And if I cancel out the h bars, I just end up with c divided by omega times delta x. And that's a rough way of working out, oops, push the wrong button. That's a rough way of working out what the width thickness of this slit is. So try doing it with a piece of glass. In fact, you can do this in an interferometer just with some water. Just put it on an optical table, flood some water in, and what you find is that the central fringe narrows, and it's narrower by the refractive index. So now you find the opening angle is c divided by n times omega delta x. Well, what's happened here? It can't be a change in the spread of your momentum in this direction, because that's fixed by the uncertainty principle, that's delta x. The only thing that's left that you can possibly have changed is the momentum in the forward direction. And so that must have increased by the refractive index. And that's the other version. That's the Minkowski momentum. Or if you prefer, just take the de Broglie relation. The momentum is h divided by lambda, and of course we know that inside of a medium the wavelength decreases by the refractive index. That's just because the light slows down, and so essentially the distance that you have to travel between to get to peaks becomes, one peak to the next becomes smaller, and it falls off in exactly the same way. So if we just using the fact that momentum is h divided by lambda, and the wavelength decreases by the refractive index, tells you the momentum increases by n. And so I suggest that's an equally compelling argument as to why this one's correct. So if the first one is wrong, you have to either ditch E equals mc squared, or Newton's first law of motion. If this one is wrong, you have to ditch the de Broglie relation. So your choice is yours.
Do you have to worry about that you're not computing lines and variance?
Nope. Why?
Well, it's a laboratory dependent.
Sure. But it's a real effect I could do in a real laboratory. And of course you could go and try and work with moving media and so on, and some people have done this, but we don't even understand stationary media. So this is the stage at which essentially I was introduced to this problem by this gentleman, Rodney Loudon, and his suggestion was, well, it may be the case that momentum is hard to understand, but we certainly have a better chance with forces. So his idea was we take the force density, we integrate up the force density inside the medium, we get the momentum, and we can work from that. And the problem is that there are two rival expressions for the force density. So and here they are. Oh, keep pushing the wrong button. So this force density, which I've put a little c on, this is based on the idea, as we'll see, of treating the medium as a collection of charges, working out the force on each of these charges, and then doing some appropriate averages to get a density. And this quantity, which is subtly different, you see this has got the divergence of p, this has got p dot del. This treats the medium as being made of electric dipoles. So it says, so if you treat the medium as an ensemble of bound charges, you get this form of the force. If you treat it as a set of neutral dipoles, you get this form. So the first problem we have to solve to sort this out is which of these forces are we going to use. So let me just show you very quickly how we arrive at them. So first of all, the charges one. This is the Lorentz force law. Incidentally, if you go back to Lorentz's book on the theory of electrons, although we usually, in the books, we see the force is charge times electric field plus velocity times, with cross product with the magnetic field, this is actually what Lorentz wrote down. And of course, they were still thinking in terms of a continuum model of materials, and so this is actually the Lorentz force law. The force per unit volume, charge density times electric field, cross product of current with magnetic field. And all we have to do is a little bit of undergraduate electromagnetism. Of course, D is epsilon E plus P. If we don't have if everything is electrically neutral, of course the divergence of D is 0. That gives me my relationship between the divergence of P and rho. I can write my current of the bound charges as the time derivative of the polarization, of course, and that takes me from the Lorentz force law to this expression, and that's my force per unit volume based on treating the medium as made of charges. to work a little bit harder if you treat the medium as being made of electric dipoles. So here's my point dipole. I can just consider one dipole. Of course, it's just a separation. I can think of it as a simple separation of charge in some direction, and this arc this is going to be the center of mass of the dipole. And here the trick is to say, well, the force on this, overall on this dipole, let's just concentrate on the electrical piece, it's going to be the charge times the local electric field. And of course, we have a positive charge up here at R plus A over 2. We have a negative charge down here. And then all we have to do is shrink the dipole to make it a true dipole by just taking the first term in the Taylor expansion of these two. The zero-order term cancels out. And the first order term gives me QA dot the divergence. Then all I have to do is add up over all of these dipoles, and I get the other form of the force. So both of them are perfectly respectable. So does it matter? Because, of course, we never really observe a force density. What we observe is a force. So when we move from a force density to a force, there's always some integration implied. You have to look at the effect on the object, a macroscopic object, a mesoscopic object, or a microscopic object. So it may be the case that the force densities are actually fine. I'm going to try this on 3 different scales, what I call microscopic, macroscopic, and should we say mesoscopic. So first of all, if we think about integrating up over the force for a single dipole, so maybe just a single atom or a single molecule, if I start off with the dipole form, of course I get back to this form. These buttons are too close together, or my thumb is too big. I'm not sure. Then you get to this form for the force on the dipole, d dot the divergence of E, d dot grad E, and then this, of course, this is the magnetic piece, as it should be. You have to work a bit harder to work with the form based on the charges, because it has this derivative of a delta function sitting inside it, but you do your integration by parts, and sure enough, the forces turn out to be exactly the same. What about the macroscopic scale? Supposing I've got a piece of material, some little piece of dielectric trapped in, say, for example, in a light field, and I'm interested in the total force on it. So this is my force, this is my material of some volume V, and I can construct this surface which contains the material. And if I do that, let me just look at the difference between the total force between this model based on dipoles and the model based on charges. And then what happens is that the dipole piece is P dot del times the electric field. The charged piece, of course, has the divergence of P. And now you can sort of see what happens, because this essentially is telling me that I can combine these two using the product rule, so that I just have a differential operator acting on P and E. And now, of course, what I need to do is use the Gauss theorem to integrate over here. And sure enough, wonderful, the forces are the same again. So if I'm interested in a small object or the total force on a larger object, both of these descriptions give you the same. What about the mesoscopic scale? So supposing this is now some material, and I'm interested in just the force on a little piece of volume here. For example, I could have a vat of liquid, and I could try and use a laser beam to push some of the liquid around. Then they're not the same, because if I look at this integrate over this volume, of course I now get a surface contribution. The polarization is not 0, and so there's a difference between these two forces. And in fact, just to emphasize this point that they're fundamentally different, if I think about an optical field, do some cycle averaging, then the dipole form just gives me the gradient of the intensity, something that looks like the gradient of the intensity. So that tells me that I suck this material in towards where a maximum of the intensity. This piece actually, if you look at that bit there, it actually depends on the direction of the electric field. This one's independent of the electric field. This one depends on the direction of the electric field. So in principle, at least, there are observable differences for these two forces. But it's an illusion. And it's an illusion because if you think about what we mean by working out the force, here's my little volume V again. I'm going to choose some point R0 sitting inside this medium, and I'm going to think of this as being just some small element of volume, and let me work out what the force is on this element of volume. Of course, as I say, I only need to think about the electric piece because that's where the difference appears between the two force densities. And if I want to work out the force on this piece of material, then I can do that by integrating up the Lorentz force density. So I can go back, here's my charge density, here's the electric field. Of course, both of these are depending on R. And in order to do this integral, of course, if you think about it, this quantity here, this rho, is changing on a dramatic scale. It changes sign at least on the scale of the distance between the electron and the proton sitting at the center. So this is a wildly fluctuating quantity. Not so much the electric field. If I'm interested in the macroscopic electric field I can see, then at least I can think of doing some averaging over this quantity. So I can write that electric field as a Taylor series in this way. And then what happens is, oh, I beg your pardon, this should be down here. This is in the wrong place. What this piece tells me, this piece down here, is that I get a net force if, because this electric field comes outside, I get a net force if the volume is not strictly electrically neutral. And if that doesn't appear, I get this contribution, with that piece disappearing, if the volume is neutral, and that's P dot del E. So the reason we have these two different definitions for the force density is very clear. And in fact, if you think back to those undergraduate lectures, you've seen this before. Because you remember when you looked at the theory of dielectrics, they do these little pill boxes and things, and they teach you boundary conditions and so on. And, and you open up one of these textbooks, and it shows you one of these volumes, and it shows you a dipole on the side with the charges pulled in and out. So you've got partly inside and partly outside. You put a field across it, and the plus charges slop outside the volume. The negative charges are inside the volume. That's what this is doing. In the dipole form, you say, well, actually, no, I'm going to every element inside this volume is strictly electrically neutral, so I can't pull the charges out. So the reason you have two different force densities is because you mean two different things by the volume. If you treat the medium as made of elementary charges, it makes sense to allow the possibility that you could stretch a dipole so that part of the charge is inside and part of the charge is outside. But if you treat it as being made fundamentally of dipoles, you can't do that. So that's what the difference is. It comes down to what you mean by the volume. If your volume is allowed to have charges or dipoles stretched across it, it no longer has to be electrically neutral. But if you average it on a different scale, so that you either think about dipoles moving inside or outside as a whole, of course it has to be electrically neutral. So perhaps rather disappointingly, although we've learnt something about dipole forces, the forces are the same. What does an experiment have to say? There's been a long run of experiments, including three definitive papers on this particular problem, one supporting the Abraham and two supporting the Minkowski, published in Physical Review Letters in the late 2000s. But I'm going to go back to an earlier experiment. This is an experiment done by this man, Alan Gibson, in the 1970s. And what they were interested in was detecting long wavelength radiation. And the problem with detecting long wavelength radiation is that it's hard to find things to absorb it. And so what they developed was what they call the photon drag detector. So this is a piece of suitably doped semiconductor. You send in your long wavelength light, and the idea is that rather than being absorbed, what it does is it transfers some momentum to the charge carriers, tries to push them. And that will induce a current. And what you do is you apply a restraining voltage to cancel the current. Oops, done it again. To cancel the current, and that's the voltage you measure. And the presence of that voltage is an indication that you have long wavelength radiation coming in. Rather a clever idea. So these were very careful guys, and what they did is they said in their paper the results were consistent with the Minkowski momentum, because the amount of momentum that was transferred to these charges was essentially consistent with it being n times h bar k. So that was the amount of momentum transferred to these charges. So they said it was consistent with the Minkowski momentum. Or in other words, that the photon momentum inside the medium is increased by this refractive index. So let's think about this, think about this thought experiment. Here's my photon coming in with this momentum. Now, for the first time, I'm going to have to be introduce some subtleties about the medium. Of course, real media are dispersive and they're absorbing, and so in fact there's not one refractive index but two. So we can think of the phase index, which is c divided by, the phase velocity is c divided by the phase index. This is what we usually mean when we say the refractive index, but there's also a group velocity which in general will be different, and that's c divided by, that's how I define my group index. So what we can do, because we have a theory of the force, is we can do a calculation, put a single particle, single photon in, and just integrate up the force and work out what happens. And this is what we find. So what we find is that the momentum transferred to the charge carriers per photon is indeed the free space momentum multiplied by the phase index. So this is the Minkowski momentum. But there's also a contribution to the bulk, which they couldn't measure. And there was a force which actually tries to move the whole material, and that's this one. And you add the two together, and you get the free space momentum, and then it's a half of multiplied by the refractive index plus divided by the refractive. So it starts to look even more complicated, because this, of course, is the average of multiplying by the refractive index and dividing by the refractive index. And it has even been suggested that that's the correct answer. It isn't. But in fact, this is very simple. It makes perfect sense because, all that is an expression of momentum conservation. It's a calculation you can do very easily for yourself. So if I just take my block of glass or material, here's my momentum coming in. Of course, there's a probability for the photon to be reflected. This is my reflection coefficient. And if that happens, I get momentum in the opposite direction. So that's that contribution. And of course, this is my transmission coefficient multiplied by whatever the momentum of the photon is. And I can, by balancing the total momentum, I can find out what P is. And sure enough, it turns out to be that. So everything's fine. What it hasn't told us, however, is why the momentum transferred to the charge carriers was as if the momentum of the photon inside the medium was multiplied by the refractive index. Now, because we have a theory, we can do things that the experiments can't do. So what we can do is we can think about a weak transparent dielectric. We can put a photon in. We can integrate up the force on the medium and look at the light going through. And if we do that, we find that in this case, the momentum of the photon inside the medium, while the photon was in there, is h bar omega divided by the refractive index times c. In this case, it's the group index. So in one case, we've got the momentum is the free space momentum multiplied by the phase index. In this case, this was the light box experiment in support of the Abraham momentum. We find indeed that momentum is indeed h bar omega divided by c times and this is the group index. And the group index is there, of course, because if you remember, a central part of the argument was how long the light stays inside the glass. And of course, that's decided by the group index, not the phase index. So at the end of this exercise, we've learnt precisely nothing about the problem. What we found is that in one case, where the experiment found the Minkowski momentum, the theory also predicts the Minkowski momentum. If we analyze this case, which was the thought experiment in favor of the Abraham momentum, sure enough, we get the Abraham momentum. So they both appear where they should, out of the same theory, which is kind of reassuring in some sense, but it resolves nothing. So at this stage, I got involved in a meeting sponsored by the Rank Prize Funds. Some of you may have come across this organization. It was an organization left by an endowment by J. Arthur Rank, him of the movies and of Frank Hovis McDougall, to support conferences in nutrition and optoelectronics. But these are conferences like you have not seen. These are conferences in 5-star hotels with all expenses paid and so on and so forth, organized by young people. And so some students or some postdocs organized this meeting through the Rank Prize Funds on precisely this problem. And the first two speakers at this meeting were Ed Hines and myself. And without having previously conferred, we both sort of decided to strip this problem down to something very simple. We both started to strip it down to turn the problem around. So instead of thinking of a pulse of light going into a medium, and the medium is not very well understood, we thought we'll think about something we really understand, which is a single atom or a dipole and a laser field, and look at the influence between these two. So Ed did his calculation and proved that the momentum transfer was the Minkowski, and I followed with the analysis of exactly the same problem and proved it was Abraham. It was the perfect start to the meeting. Now I have to choose my words carefully. Let me see. Modesty forbids me from saying who got it right. Yes, I think that's the right way of saying it. So what we're going to do is we're going to assume that the atom is very far from resonance. So essentially there's no absorption, no scattering, no spontaneous emission. So it behaves like an elementary piece of dielectric transparent medium. And the idea is to calculate the transfer of momentum to the atom and then use momentum conservation to work out what the momentum of the light is. So let me go back. We're going to use the Lorentz force law, and there's a little piece of analysis very simple analysis we can do on this form. This is the force on a dipole, and for sure our atom is an elementary dipole. And we can just apply a little bit of elementary vector calculus to rewrite it in this form. So here we've got d dot, the derivative of the electric field, and then a time derivative of the d cross b. And this time derivative piece turns out to be the key to understanding what's happening. So first of all, let's look at just the first term. And the reason why it might be reasonable to look at the first term is that if we're in an optical field, which is oscillating at some high frequency, and we do some cycle averaging, essentially the response of the dipole goes like the electric field, and so on cycle average terms, this is tiny, because it's essentially the product of a field and its complex conjugate, and it's quasi-monochromatic field. So reasonable to drop that piece, and that's what's always done in laser cooling experiments, for example. And if we concentrate on the first piece, what we find is that there's a force which transfers this amount of momentum to the dipole. And if we go along, if we analyze it in terms of an effective one-atom dielectric constant, we find that the atom is sucked into the field, and the fact that it's sucked into the field means that momentum conservation says that the momentum of the light is increased very slightly, and that turns out to be consistent with the Minkowski interpretation. What about that piece up there? Well, the interesting thing about this piece is that although it's everywhere tiny, if you think in terms of the envelope of this field, all the time that the atom is going into it, the field is increasing. So although the derivative is tiny, it's integrated up throughout all the time that the atom is going into the pulse. And what you find, remarkably, is that when you do that integral, this quantity is opposite in sign to the first piece and double in magnitude. So it changes the sign. The atom is pushed out of the field, and this gives you the Abraham result. So that's the degree of subtlety that comes in. Okay. So it really looks as though, after a decade of thinking about such things, it looks as though what we've got is a theory which matches with the experiment and no insight at all as to why there are two momenta. So in some ways a rather disappointing result. So we got to thinking about whether it was possible that rather than one momentum being correct and the other one being wrong, which had been the argument since 1909, perhaps they were both correct. And so we scratched around and looked for places where you have two correct momenta, and it wasn't hard to find one. Because, at least in quantum mechanics, and indeed in, certainly familiar in quantum mechanics, it arises in classical electromagnetism as well, there are actually, in the interaction between charged matter and light, there are two distinct momenta. There's the kinetic momentum. So for an atom, this would just be the mass of the atom multiplied by its velocity. And there's also a canonical momentum, which essentially is h divided by lambda or h bar k. And when we look at the interaction between between the charged matter and the light, these two quantities are not different. So how are they different? Well, it certainly depends on the form of the gauge and so on that you use. But essentially, if we go back to thinking about dipole coupling, electric dipole coupling, then what we find is that for our atom, the kinetic momentum is the canonical momentum plus the cross product of d with the magnetic field or the magnetic induction. Of course, this is this piece that arose in the dispute about the force on the atom, the time derivative of this. So it's precisely this momentum that appears. So this is what we find. Mass times the velocity of the atom is P plus this D cross B piece. And that's essentially the key step. Because if I think now in terms of the integrated momentum density, if I look at the Minkowski momentum, that was this D cross B, the displacement field cross product with the magnetic induction for my electric dipole atom. What I get is I get the Abraham form plus this bit. This is this dipole, the polarization, of course, is just the dipole multiplied by essentially a delta function sitting on the position of the atom. So that's how they're connected together. And if I add the kinetic momentum of the atom to the total Abraham momentum, I get the canonical momentum of the atom plus the Minkowski momentum. And so, actually, things start to look rather reasonable. We get a single conserved total momentum for the matter and the field, but we can partition it in two different ways. We can slice it up so that we have a kinetic momentum for the atom and what we must associate with the kinetic momentum of the field, and a canonical momentum of the atom, and this piece must be the canonical momentum of the field. Why does this appear? Well, it appears because of this contribution has both a field, it has a magnetic field, and it has a dipole. So it has both matter character and field character. And so if we're interested in trying to partition the total momentum, we have a choice about where to put that. Clearly it must be in the total, and we can associate it with the atom, in which case we get this piece, or we can associate it with the field, in which case we get this breakup. It doesn't tell me yet why I seem to see one of these momentum in some experiments and the other momentum in different experiments. That we have to come to. But it does at least provide a total momentum and the identification of kinetic momentum with the canonical momentum. This is don't need this. This is just if you put in magnetic dipoles as well, magnetic dipole as well as an electric dipole, then you get a distinction between B and H, of course, and it goes through in the same way. You still get a relationship between the Minkowski and the Abraham momentum plus polarization broken up in this way. But that's too much information, I think. So are we finished? No. There are two remaining problems, and two remaining problems which could destroy this simple association if we can't solve them. So the first one, and indeed the most important, is we've decided that one of these momentum is a canonical momentum, the other one is a kinetic momentum. But in order to be useful, I have to be able to say to you, in one particular type of experiment, you will see an expression of this momentum. In a different type of experiment, you will see the expression of the other momentum. Otherwise, it's a useless concept. So it's almost a rephrasing of the problem. And the other one, which is at first sight looks more serious, is that the ideas don't match. I'll show you why. So if we go back to this idea that the Minkowski momentum is D cross B, the Abraham momentum is E cross H, and compare with what we now have, so we had, when we did our analysis, we found essentially Minkowski momentum behavior was H bar omega divided by C multiplied by the phase index. The Abraham momentum was H bar omega divided by C, and it's the group index that sits on the bottom. So our analysis based on the forces has suggested that the relationship between the Minkowski and the Abraham momentum is given by the product of the phase and the group indices. Fine. But if you go back to D cross B and E cross H where we started, the fact that the D is epsilon times E, B is mu times H, so the relationship between these two is the square of the phase index. And these two, of course, are not the same. The group index can be fantastically different from one. Just to give you an example, in slow light experiments, the phase index in cold gases, the phase index is essentially 1. The group index can be 3 times 10 to the 7. You can slow light down to the speed of a bicycle or slower. So they can. The difference between this contribution and that can be 3 times 10 to the 7. It could in principle even be 3 times 10 to the 8 or even infinity. You can stop light stone dead. So it's a problem. At this stage, this was spotted a little while ago, 2004, and it was even suggested by these authors that what you should do is have not 2 momenta but 3. You should have a canonical, an Abraham, a Minkowski, and a canonical momentum. And that way lies madness. If you make up a new momentum for each thing you calculate, then the momentum ceases to be a useful concept. Okay, so that's where I sort of lower my voice a little bit, and I'll tell you how it all works out. So at the bottom of this is a recognition that it's not just that you have these 2 different momenta, but you have to think a little bit about what canonical and what kinetic momenta actually do for you in a theory. What's their purpose? What's their role in life? And in order to show where the problem arises, the first thing I can do is to calculate these 2 momenta, these Abraham and Minkowski momentum, as I would get it if I just integrated up over E cross H or D cross B inside my medium. And what I find is that the Abraham momentum does indeed turn out to be h bar omega divided by the group index times c. And of course, if you recall, this was so E cross H for the momentum density matches with h bar omega divided by group index times c. The problem is with the Minkowski momentum. If I integrate this object up, I get what I'd like to be the Minkowski momentum, but it's multiplied by the ratio of the phase and the group indices. So this is where the problem lies. Now, the issue is, it's silly. I should never have calculated this expectation value in this way, because that's not what a canonical momentum does. It's fine to calculate the expectation value of the kinetic momentum. This tells me about how much momentum, how much push the part of the photon has. It would make little difference as far as this calculation is concerned if I was talking about a photon wave or a bullet. It's how much kinetic kick that I have. But the role of the canonical momentum is nothing to do with expectation values. It's supposed to sit in commutation relations. It's a generator. The canonical momentum is not something to calculate the expectation value of. It's the generator of translations. So let's try that. So essentially, it's the same. It has the same role as the canonical momentum minus I h bar d by dx has in this material commutation relation. It generates an infinitesimal translation in position for me. So if I take my canonical momentum, d cross b, my Minkowski momentum, and look at what happens if I make a translation on one of the fields, this is the vector potential, I find that sure enough, I get this translation from A of r to A of r plus A. And if I think about that in terms of just a single plane wave component, the e to the ikz, what that tells me is I've changed e to the ikz to e to the ikz plus A. I've got this displacement sitting in here. And of course, k is just the phase index times h bar omega over c. And that's the right answer. So although if I take the expectation value of d cross b for my single photon pulse, I get something that looks wrong, if I put it in the commutation relation, I get the displacement by the right amount. So why this difference? Yes, no, it is indeed. It's not the expectation value of d, but when you do the commutation relation, it gives you the right piece. Why? Well, fundamentally, it's because something again which we all know, and it's one of those sort of those moments that you laugh out loud or call yourself an idiot, whichever way around it is. Because, of course, one of the problems which has underlined all of this is that if the light's inside the medium, we probably shouldn't think about photons at all. We should think about polaritons, because it's coupled excitations of the light and the matter which are our fundamental description. So what happens if this is a very simple Hopfield type dispersion curve, and I can think about just a single K, a single wavelength, and in this case I have 2 branches, down here the acoustic branch, up here the optical branch. And if I put some light in at this frequency, essentially what I do is I put an excitation here. So this is my photon-like excitation. So when I talk about a photon traveling in a piece of glass, that's really what I'm talking about. This mode down here is unoccupied. That's where the energy goes. Oops. Yes. That's where the energy goes. This piece doesn't enter into it. So if I take the expectation value of my momentum, I get a contribution from this branch, but I don't get a contribution from that branch. But if I calculate a commutation relation, so here, for example, this is a Coulomb gauge relationship between the vector potential and the displacement field with our transverse delta function. If I break this down into all of the polaritone contributions, then for a single value of k, it has two pieces. It has the ratio of the phase and the group index at that frequency, but it also has a contribution from this frequency. Oops. And so that's the optical part, that's the acoustic part. And by virtue of a rule which you can derive for a medium based on very general principles of causality, the sum of the ratio of these two has got to be equal to 1. So what's really happening is that in the commutation relation, all of the polariton branches contribute to give you the right displacement. It doesn't matter whether they're occupied or not, it's about commutation relations. But if you take an expectation value, then only those polariton modes that are actually occupied will make a contribution. So the mistake is to take the expectation value of a canonical momentum. That's not what it does, it's the generator of translations. So why are there two momenta? How does it hang together? And also, finally, the most importantly of all, when I do an experiment, which of the two should I expect to find? So we can answer that too. So remember that we started off with this idea. This was my first explanation, my first analysis, and this was based on the center of mass energy. And we found there that the conservation of momentum told me that I should expect to see the Abraham momentum. And that's now reasonable, because this is, if you like, this is a particle property. This doesn't rely on the wave nature of the light at all. In some sense, this is, as I said, I would get exactly the same result if I did the analysis with bullets rather than with photons. So it's a particle property, i.e. a kinetic property. When I looked at the diffraction inside a dielectric medium, I found the Minkowski result. Of course I did. It's a wave property, h over lambda. So if you like, the language is a little bit loose. Where I investigated particle property of light, I should expect to find the Abraham momentum. When I look at a wave property, I should expect to find the Minkowski momentum. That's almost the end of the story. But you remember that in the photon drag detector, when the light went into this medium, it transferred momentum to the charges as if it were the Minkowski momentum. Why is that the case? Well, this is just the final caveat. If I'm looking at displacement within a medium, so for example, if I think about hanging a mirror in some liquid and shining a light on it and working out what the momentum transfer is. So you think the light comes in, it's reflected, there's going to be a kick on the mirror, and the kick on the mirror will be twice the momentum of the photons. Which would I expect to see? The particle one or the wave one? Well, actually, it's the wave one. Why is it the wave one? It's the wave one because what you're doing is you're trying to induce a translation of this object inside the medium. So it's the displacement within a medium. You expect to see the Minkowski momentum. So in other words, an object which is embedded inside a medium will receive the momentum as if it were the Minkowski momentum. So, just a little final note on this. Remember I said that in slow light media you can have these extremely large differences between phase and group indices. So some collaborators in Ottawa are setting up an experiment in a cold light medium in a gas with little dielectric spheres and shooting light up at them to see how much light is required to move the objects. And as I said, there should be something like a factor of, say, 3 times 10 to the 6 between the two different predictions. So I'm hoping the experiment will come out in favour of what I've just said, otherwise I have to can all this and start again. So let me conclude then. So the story starts, as I said, these two rival momenta, and you'll find a long literature throughout the 20th century with a humbling number of contributions from well-known authors on this topic. But at the base of it is this question of does the momentum of light inside a medium increase or does it decrease? And if the Abraham momentum is wrong, then you essentially have to can Newton's first law of motion, which would be a disappointment. If the Minkowski is wrong, then you have problems with the uncertainty principle, diffraction, and actually the Doppler shift, which can be measured, comes out the wrong way around as well. The Doppler shift inside a medium comes out wrong too. So on the basis of that, the conclusion has to be that they're both correct, and they are. And the only subtlety is that in order to make these two fit with the E cross H and D cross B, you have to recognize that this is the kinetic momentum, this is the canonical momentum. You take the expectation value of this one, if you want to calculate the amount of punch that the light generates. This one is designed to sit in kind of commutation relations. And if you don't forget that, plus the fact that light inside a medium, electromagnetic field inside a medium comprises polaritons, then you're home free. So thank you all for your attention.
Steve, your stimulating contribution is now open to questions.
You discuss non-magnetic dielectrics. If there is magnitude, does it add some additional confusion?
Yes. I'm just plugging away. Yes. Absolutely. So the analysis here was all about the difference essentially between D and E. If you go back to this analysis, if you go back again thinking about just a single point dipole, and if it's a magnetic dipole rather than an electric dipole, then the same thing happens. So here you get, instead of D cross B, you get M cross E as a contribution. And again, integrating it up, this piece, when added to that one, gives you precisely the piece that you need in order to make the difference between D and H. So everything hangs together. This being the associated momentum for a magnetic dipole inside an electric field. Yeah.
The relation between your two momenta is a gauge transformation. Exactly a gauge transformation. D goes to D minus A.
You can think of it that way. I prefer to phrase it slightly differently, if I may. I think the kinetic momentum is the kinetic momentum. The canonical momentum, of course, is gauge dependent.
Yeah, the two are connected by a gauge.
Of course, they're connected by a gauge transformation. That's right.
Which is entirely consistent with what you're saying. Gauge transformations don't change physical space.
That's right. Yes, that's right. Okay. Yes, if you want to, I mean, yes. Right. So, for example, if you look at it in terms of minimal coupling, for example, rather than electric dipole, you get a different formulation. That's correct. Yes.
So then, can I say, what you're telling us is that different physical problems have sort of natural gauges,
yes,
better ways to think about it.
No, that is definitely true. If you have bound neutral matter, and if you're not in the relativistic regime, it's certainly true that things come out more naturally if you use electric dipole coupling rather than you don't have to worry about the A squared term and so on and so forth. And there are other more profound reasons for preferring it. But you could, of course, it is a freedom. So you could work with a different canonical momentum. Absolutely, yes.
Martin?
I have this sort of small experiment in mind, which I thought I knew the answer, but I'm not perfectly sure. Suppose you have a liquid water, it will do fine, and you shine a laser light on the surface. What will the surface do?
Oh,
I thought it will go up.
It will. It will. This is a sort of classic experiment. It was done by, I think, first. Is there some chalk? Yeah. It was done first by Art Ashkin, and caused an awful lot of arguments. So just just for those who are not familiar with it, very simple idea. You focus some laser beam like that. Light diffracts and does things and so on. So that's essentially what it looks like. And the question is very simple. You shine the light on the water. Does it bubble up or does it push down? And you might think, well, it's carrying a lot of momentum, so it will make a dip. It doesn't. It does. It produces a measurable blip. I exaggerate. And the remarkable thing is you get the same behavior whichever way you point the light. So it doesn't matter if you push the light down on the surface or from inside the medium, and so on. And so the question is why? How can you understand this in terms of the momentum? Well, fundamentally, there is a long literature, and it's a contentious thing, and of course theorists love to argue about such things. But the simplest explanation is nothing to do with the force in this direction at all. And it's everything to do with the fact that a real beam of light has got an intensity distribution across it. 0 outside, and has this peak in the middle. And what that means is that there's a force on the surface, on the liquid, towards the center. So rather than thinking in terms of the push in this direction, think of a tube of toothpaste. Essentially what it's doing to the water is it's pulling it in, and the water's only got one place to go. So that's my best understanding of what's happening.
You could also understand it in terms of Minkowski momentum, including the reflection.
Yes, you
part
can.
of the
Yes. If you want to.
Works perfectly well with Minkowski.
And I'll give you another example as well, if I may. Have you heard of something called an optical stretcher? No? It's a lovely idea. It works on single cells. Essentially what you do is you put 2 counter-propagating beams, I just draw them like this now, 2 counter-propagating laser beams, and you put your cell inside, and what happens to it is that it goes from this to that, like that. And you might ask, why is it, essentially, and of course that's also explained in terms of the Minkowski momentum, and you might ask why. And the answer is the same in both cases. It's because what's happening is refraction. So it's actually the redirecting of the light field. You can see in here, if I put my light coming down, what's going to happen is it's going to refract in. It's the refraction of the light, and refraction, of course, is a wave phenomenon. And so it's a wave phenomenon. You tend to find the Minkowski momentum. But that's just my best current insight.
Yes, a quick observation and a question. When you talked about the difference in the forces between when the volume is electrically neutral or not electrically neutral, so if I look at this, say, from the point of view of Poisson's equation, so I just write the Poisson's equation for the system, so I get electron neutrality, right, if I put the dielectric coefficient equal to 0. Of course, we know that this is not a very precise thing to do, but in electrochemistry, is when people say, well, if you are above a few nanometers, that divide length, so then it's okay to consider to assume electron neutrality, and then you have the boundary layers, say, near surfaces at an interface that separates, say, 2 different dielectric that have charges. So what I find very interesting, and at this point, perhaps it's something I am fully misunderstanding, is that in the first place, to really say that, okay, to get these conditions, I have to go to the limit, the dielectric coefficient 0, right? So just again, the Poisson's equation argument to get electron neutrality. But then my question is, if I have a system with different pieces, say different kinds of ions, right? So what is the right way to calculate the dielectric coefficient?
Oh my gosh. Yes.
So does it have any relationship with the way that, say, Abraham and Minkowski calculate forces, or is something independent? So does your theory say anything about this situation?
No, but I may be able to help. So, of course, if you have free charges, essentially, or separable charges like ions or something of this kind, then what you also need to include in your force law are the forces on the free charges. And there it becomes rather like with the issue of these 2 different force densities. It becomes a matter of how you do your averaging. So, do you allow? Do you insist that you have, like in the photon drag detector, where you have these free moving charges? Do you insist that your averaging is done such a way that each volume is strictly neutral, or do you allow, or is it part of the physics, the separation of the charges? And of course, that's the distinction which you have to judge. It comes down to how you define the averaging. Well, rather like with this dipole argument, where you allow the charges inside out. So the most important question, I think, is when you say you have a force density, you have to think most carefully about how you define the conditions on the volume. And I think that's true if you've got free charges as well as if you've got just bound charges. But precisely how to.
In your description of the kinetic and other parts, I mean, you basically said the atom can be described by a point dipole.
Yes.
What happens if you now have to include quadrupole moments? Because, I mean, the electron density can be deformed, and it's not, I mean,
linear part is sometimes sufficient, but in strong fields you might need to take into account quadrupole moments. Can you carry on your description further on, include higher and higher order moments?
Yes, I mean you can precisely, and in fact there's a within the theory of the non-relativistic theory of light matter interactions, there's a whole hierarchy in terms of this, and of course there are quadrupolar and higher order moments, of course.
That means also what is correct. I mean, if you say correct is only we stop at the limit of maybe stopping at dipole moments. I mean, the correctness would mean just go to infinity and sum everything up.
I'm not sure, to be honest. I mean, if you think about the scales involved, for example, if you look at this dipole series, so the small parameter that enters into this is the ratio of the size to the wavelength. And so, of course, there are fields, nuclear physics, for example, where the whole multipole expansion is kind of important. But for the most part, in optics, it really isn't. You've got a factor of, at least 1,000 is the size of your scale. So although you do get quadrupolar transitions, you tend to get them only when the dipolar ones are not present. And if you're talking about a medium, there are always some dipole transitions around which are around. So I can't give a definitive answer. I mean, I can see how to put it together. Although for the situations we're interested in, the effects are tiny.
I'm afraid it's the last one, Tim.
Yes. Are there the other things that happen in the kind of media that we are used to is that they are chiral and particles polarization rotates and there's presumably transfer of angular momenta. Are there any, and of course you might get Faraday effects and stuff like that, are there any related problems associated with angular momentum that are analogous?
Yes, there are, very much so. Just give one example. I mean, it's a whole area, of course. I'll just give one very simple example, if I may. So you could ask the question: if you've got you can make a helically phased light field, something where the phase depends on the azimuthal angle, and this carries orbital angular momentum. So I can ask the question: if I make one of these things, they're going to look a bit like a donut. There's no light in the middle because there's a phase singularity. I can take one of these beams and I can focus it down on a little bit of glass like that. And I can ask a very simple question. When the light goes in, does the bead start rotating or not? And it turns out that if you do the sums, you find that the Minkowski and the Abraham, because you've got two factors going on now, you've not just got the momentum, you've also got refraction at the surface. And it turns out that the Minkowski prediction is that you get a cancellation and there's no rotation at all. And in the Abraham one, you get a rotation. So you can think about it. The pulse of light comes in, starts rotating, so you get this sort of gyroscopic rotation. And we did the experiment. We tried it. And the problems with the experiment are, well, first of all, you've got to make the light pulses very short. You've got to make them very short because you need to make sure the light's inside the glass rather than most of it outside. And you've also got to make the object very small because, of course, if you make it very big, the moment of inertia is enormous. You won't see anything. So we did our best. What we ended up with was probably the UK's most expensive glass melter. Because what we ended up with was an awful lot of molten beads of glass. So the jury's still out on that one. We were expecting to see the rotation, but the experiment didn't work because, well, you get a small amount of absorption in glass. It's tiny, but it's enough to melt the glass. So we'll try again sometime maybe we'll get a better material.
Also cause Minkowski type rotation.
Sorry?
Absorption will also cause Minkowski type rotation.
Oh yeah, I mean, we thought this was a great idea because we thought if we can do without rotation, the reason why we first thought about a rotation experiment, of course, is because you put your light down on the material, and of course you get this transfer through, but you also get reflection off the top. And reflection off the top is one of the things that makes it very hard to look at a straight translation experiment. Even a small amount of reflection will kill you. But of course, reflection off the top doesn't change the torque. So we thought, great idea. And we sort of hoped the absorption would be small enough that we could actually tell the difference. But as I said, there was enough absorption to melt the glass. So it's just, just badly wrong. So that's just one example. I mean, but you're right, there's a whole field of chiral molecules, chiral interactions and so on, where things get much more interesting. Of course they do. Here I've, strictly speaking, got a dipole moment which is always proportional to the electric field. It's the simplest possible case, but there are much more interesting materials, as I've been learning from Epiphania in the last day and a half.
Thank you very much, Steve.